The solar wind slammed into Earth's magnetic shield at 1.34 million miles per hour. That's fast enough to cross the United States coast to coast in under 12 seconds. The agency that forecast it called a G1. It arrived as a G2. NOAA's Space Weather Prediction Center had issued a G2 moderate geomagnetic storm watch on April 16th. The internal models had originally forecast a G1 minor event, which sits at a KP index of 5. The actual reading came in at KP6. That's one full step up the scale, and the watch was upgraded after the stream had already made contact. The source of the storm was a coronal hole. That's the plain name for a dark opening on the sun's surface where the magnetic field lines spread apart and release solar wind straight into space. This particular hole moved into an Earth-facing position during the week of April 13th through April 17th, 2026. By the time the watch was upgraded, Earth's magnetic shield was already absorbing the blow. Normal solar wind moves at 350 to 400 kilometers per second. This stream hit 600 to 700. It held that speed for 4 consecutive days. Not a burst, a sustained push. Before we go further into what the forecasters missed and why, take a second to subscribe to the Science Studio so the next one of these events reaches you before the news cycle catches up. And drop your location in the comments because this storm didn't hit every region the same way. If you saw Aurora from a backyard that's never seen it before, we want to know which state. The timing is the part that changes everything. The G2 watch went out on April 16th at 02:25 UTC. The storm began on April 17th. Confirmed readings showed it was still active on April 19th, and the disturbance carried into April 20th. That's 4 consecutive days of elevated geomagnetic activity, which is an unusually long run for any solar wind event. NOAA's own public forecast gap was the story before the Aurora was the story. 7 states saw Aurora that NOAA's forecast said wouldn't see any. That gap between prediction and observation is confirmed. It didn't happen because the hole was bigger than expected. It happened because something arrived before the mainstream did. Most people assume space weather forecasts work the way ground weather forecasts work. The agency issues a watch. The watch describes what's coming. You plan around it. That assumption held for decades, and it's the mental model most viewers still carry when a space weather alert crosses their phone. NOAA's model said G1. The storm arrived at G2. 1 kp level sounds small on paper, but it means Earth's magnetic shield compressed an additional 20,000 kilometers inward. That's roughly the distance from New York to London, pressed against the planet. For a viewer in Minnesota, Wisconsin, or Pennsylvania, that inward shove pushed the southern boundary of Aurora visibility several hundred miles south, well past their backyard. The forecast didn't fail because the hole was larger than expected. It failed because something else arrived first. The coronal hole itself is worth picturing clearly. It isn't a burst. It isn't an explosion. It's an opening. The magnetic field lines that normally loop back down into the sun simply don't close. They stretch outward into space, and plasma flows out along them at high speed. When that opening rotates toward Earth, the stream pours straight at the planet like water running downhill. The duration depends on how long the hole stays in an Earth-facing position, which is typically several days. This event lasted 4. That's on the long end of what a coronal hole stream can produce, and it matters because every system that absorbs the stress absorbs it repeatedly, not once. The speed of the wind is only part of the picture. Density matters too. The stream compressed the solar wind ahead of it, creating a denser wall of plasma than the magnetic shield is designed to handle at baseline. That wall is part of what caught the forecast models off guard. NOAA confirmed the event type as a CHHSS, which stands for Coronal Hole High-Speed Stream. That's the agency's official classification for this kind of storm. The CHHSS classification is known. It's been tracked for years. What the forecast missed was the intensity, not the category. And the intensity is what determines what happens on the ground. At G1, the expected effects are limited. Weak power grid fluctuations possible. Minor impact on satellite operations possible. Aurora visible at high latitudes only. At G2, the effects step up. Power systems at high latitudes can see voltage alarms. Satellite orbits shift from increased atmospheric drag. Aurora pushes south to the mid-latitudes. This event hit G2. 7 states saw lights that the original watch said weren't coming. The jump from G1 to G2 isn't linear. It's a factor increase in the current pushed through long power lines. It's a measurable reduction in GPS accuracy. It's an extra round of corrections every satellite operator has to issue. Those effects don't wait for the watch to upgrade. They arrive when the wind arrives. For a viewer watching this at home in the northern half of the United States, the 4-day window between April 17th and April 20th was the period when your GPS drifted, your regional grid absorbed uninvited current, and the satellites you rely on for phone signals, weather data, and navigation made small corrections without announcing them. You didn't feel any of it directly. The systems handled it quietly. That's what they're designed to do at G2. What they aren't designed to handle quietly is a G3 or G4 on aging equipment, and the same coronal hole that fired this stream will rotate back into an Earth-facing position in 23 days. The Sun's rotation is roughly 27 days as seen from Earth, which means these features return on a predictable schedule. The hole doesn't close because the storm ended, it just points somewhere else for a few weeks. NOAA's SPACE, Weather Prediction Center, is the agency responsible for issuing the watches, warnings, and alerts that grid operators and satellite operators use to prepare. The agency's 3-day Geomagnetic forecast tool is the primary public-facing prediction instrument. It's the tool the watch was based on. It got this one wrong by one level, and the gap has a specific technical cause that goes beyond the hole itself. The first thing to arrive wasn't the solar wind at all. The first thing to arrive was a compressed wall of plasma that doesn't show up in the public forecast tool the way the mainstream does. That wall is called a CIR, short for Corrotating Interaction Region. It formed ahead of the high-speed stream, and it hit Earth's magnetic shield hours before the main wind arrived. A CIR forms when fast solar wind catches up with slow solar wind ahead of it. The slow wind can't get out of the way fast enough, so the two streams collide. The collision compresses the plasma into a dense wall. That wall travels outward from the Sun along with the mainstream, but because it sits at the leading edge, it reaches Earth first. The viewer assumes the solar wind hit Earth like a single wave. One event, one arrival, one impact. That's the standard mental model. Two separate structures arrived, one before the other. The CIR hit first, the way a pressure wave arrives before a hurricane's wind. The mainstream followed within hours. NOAA's forecast was built around one structure. Two arrived. The second assumption was that the models would catch the difference and upgrade the watch before impact. They didn't. Not in time. NOAA knew CIRs were possible with this event. The question isn't whether they knew. The question is what the 3-day forecast tool actually measured and what it didn't. The 3-day forecast tool is calibrated primarily for CME events. CME-driven storms are single-burst events. A chunk of plasma launches, travels, and arrives. CHHSS events don't behave that way. The stream is continuous, not a single chunk. The CIR that forms ahead of it is compressed plasma, not a burst of ejected material. The instruments that watch for CMEs don't read CIR density, the same way they read CME mass. That's the calibration gap. NOAA's own documentation of the CHHSS category treats the CIR as a contributing factor rather than a primary forecast driver. The 3-day outlook assigns a KP prediction based on the stream's expected speed. When a CIR arrives ahead of the mainstream and pre-disturbs the magnetic shield, the shield is already under stress when the main wind arrives. The combined effect exceeds what the stream alone would produce. The model didn't add the two effects together with enough weight. The real storm did. That's why the watch went out at G1 and the impact came in at G2. The CIR's job, from Earth's perspective, is to pre-stress the shield. Think of it the way a boxer's first punch sets up the second. The first blow lands, the guard drops slightly, and the second punch finds an opening. The CIR lowered the shield's resistance and the mainstream pushed through the gap. By the time NOAA's sensors at the L1 Lagrange point read the incoming mainstream, the shield was already compressed. The upgrade to G2 happened after the impact had started. The L1 point is worth knowing. It sits roughly 1 million miles sunward of Earth. That's where NOAA's primary space weather satellites, including DSCOVR and ACE, measure the solar wind before it reaches the planet. The distance gives forecasters between 15 and 60 minutes of warning for fast-moving events. For a CIR riding ahead of a CHHSS, that window is the entire lead time. There is no earlier warning buoy. 15 to 60 minutes is not enough time to upgrade a public watch, push the upgrade through operational channels, and have utilities adjust grid settings in response. NOAA confirmed the CIR, and the high-speed stream arrived in close succession during this event. Their combined effect pushed the storm one full KP level beyond the original G1 forecast. That's the specific mechanism behind the failure. It isn't a failure of observation. The sensors read what arrived. It's a failure of prediction, because the 3-day tool underweighted the CIR's contribution. This event type is one of the hardest for current models to forecast accurately at KP level. That's not opinion. That's a confirmed limitation in NOAA's public forecast system, and the agency acknowledges the gap in its own technical documentation. The gap exists because CHHSS events paired with CIRs don't produce the same signature as CME produces, and the public forecast tool was built around the CME signature first. The agency's 3-day forecast serves the grid operators, satellite operators, airline dispatchers, and emergency managers who plan around space weather. When the forecast underpredicts by a full KP level, those planners receive a watch that doesn't match the storm they actually encounter. For a grid operator in Minnesota, a G1 watch calls for routine monitoring. A G2 watch calls for active load balancing. The gap between those two responses is the gap the CIR created. In this case, the upgrade came after the storm had begun, which means the response window was shorter than the storm's first hour on the ground. NOAA's forecast tool has a known blind spot for this exact event type. Density is the word that matters here. A dense CIR behaves differently than a thin one. The denser the wall of plasma ahead of the stream, the harder it hits the shield when it arrives. Density measurements from the L1 satellites during this event showed values above the model's expected range. That data arrived in real time, but the public watch isn't updated in real time at the same speed the data is collected. The lag between observation and public communication is one of the structural limits of the current system. The gap between what the instruments saw and what the public watch said is 1 KP level. At G4, that same gap doesn't have a cushion. NOAA's space. Weather Prediction Center operates as a branch of the National Oceanic and Atmospheric Administration. It's the federal agency that issues space weather watches, warnings, and alerts for the United States. The agency coordinates with partners including the US Air Force and international space weather organizations. Its forecasts feed directly into the North American Electric Reliability Corporation's grid alerts and into satellite operator procedures. When the agency's forecast misses by a level, every one of those downstream systems receives a signal that's off by the same amount. A single off-by-1 level miss is absorbed by the grid at G2. The grid is designed with margin. The margin is there for exactly this kind of forecast gap. What happens when the miss sits at G3 or G4 is a different question, and the grid's margin shrinks fast as the KP index climbs. The shrinkage isn't linear. The current pushed through transmission lines during a G4 is roughly 10 times what's pushed during a G2. The transformers at the ends of those lines are not 10 times stronger than they were during a G2. They're the same transformers. Many of them are decades old. Some of them are older than the agency that forecast the storms hitting them, the CIR and the CHHSS paired. The forecast tool didn't fully account for the pairing. The watch upgraded after impact. The grid absorbed the stress quietly at G2 level. All of that is confirmed. What remains unconfirmed is how the same mechanism behaves when the forecast misses on a stronger storm. NOAA's post-event records for the October 2003 CHHSS storm document Aurora, reaching 34 states during a similar CIR paired upgrade. 34 states. That number sits in the historical record as the high water mark for recent CHHSS Aurora spread. This event reached 27 states. Both numbers tell you something the forecast tools can't tell you directly, because the Aurora's southern boundary is a live readout of how far Earth's magnetic shield has been pushed inward. Most people picture Earth's magnetic shield as something fixed, a permanent wall sitting at a set distance around the planet, always the same shape, always the same size. That's the mental picture from high school science textbooks, and it's the picture most coverage of space weather reinforces. The boundary moved 35,000 kilometers closer to Earth during this storm. 35,000 kilometers is roughly the distance you'd travel circling the planet at the equator. The shield didn't flex slightly. It moved the entire circumference of Earth inward. GPS satellites sit at 20,200 kilometers. The compressed shield boundary during this storm sat at 30,000 kilometers. Every GPS satellite in orbit was operating inside a zone of disturbed magnetic field. That's the same zone where charged solar particles were actively flowing. 27 states saw the aurora. That number is confirmed, but the original forecast said 20. Under normal conditions, the magnetosphere extends about 65,000 kilometers toward the Sun. That's the sunward boundary, and it sits at roughly 5 times the diameter of Earth itself. Earth's diameter is about 12,700 kilometers, so 5 times that puts the shield boundary out past 60,000 kilometers on a quiet day. Under G2 conditions, that boundary compresses inward to approximately 30,000 kilometers. That's less than half of where it normally sits. The compression happens because the solar wind's pressure pushes the shield inward until the shield pushes back with equal force. When the wind gets faster or denser, the balance point moves closer to Earth. 30,000 kilometers puts the shield boundary inside the orbital zone of high-altitude GPS and communication satellites. GPS satellites operate at 20,200 kilometers. That altitude is normally well inside the protected zone. During this storm, those satellites were sitting in a region of disturbed magnetic field instead of a quiet one. The effect on the GPS signal was measurable. GPS signal degradation was confirmed during the G2 peak. The signal didn't drop, it drifted. The timing signals that GPS receivers use to calculate position arrived slightly delayed or slightly distorted as they passed through the disturbed region. NOAA confirms GPS accuracy drops measurably during G2 conditions. The shift runs on the order of meters for consumer receivers in smartphones and cars. Higher-end receivers with multiple frequency bands correct for most of it. The shift is measured in meters, not miles. At G2, the drift runs on the order of a few meters for consumer GPS. That's enough to matter for lane-level navigation and automated driving features. It's not enough to send a user to the wrong city. Low Earth orbit satellites felt the storm in a different way. These are the spacecraft operating between 200 and 2,000 kilometers altitude. That zone includes most Earth imaging satellites, several communication constellations, and the International Space Station. During this event, increased atmospheric drag was confirmed on satellites in that range. The drag comes from atmospheric expansion. When solar energy heats the upper atmosphere, the atmosphere expands outward. Air molecules that normally sit below a satellite's orbit rise up to meet it. The satellite moves through thicker air than its orbital calculations assumed. Thicker air means more resistance. More resistance means the orbit decays slightly faster than scheduled. The decay isn't dramatic at G2. It's a small adjustment to altitude and a small adjustment to trajectory. Satellite operators run the numbers, and the ground station calculates a correction. The correction is applied through a thruster burn or an orbit adjustment. The propellant the satellite burns to make the correction is propellant it can't use later for a different maneuver. Every low Earth orbit operator managing a constellation during this event had to calculate those corrections. Some applied them during the storm, some waited until after. Either way, the storm added an unplanned item to every operator's maintenance log. The magnetic shield's compression doesn't stop at the satellite altitude. It continues down toward the atmosphere, where the field lines funnel charged particles toward the poles. Those particles follow the field lines down into the upper atmosphere, where they collide with oxygen and nitrogen atoms. The collisions transfer energy to the atoms. The atoms release the energy as light. That light is the aurora. The aurora is not decoration. It's the visible signature of energy crossing from the solar wind into Earth's atmosphere through a compressed magnetic shield. The color depends on which atom is releasing the energy and at what altitude. Green comes from oxygen at lower altitudes. Red comes from oxygen at higher altitudes. Purple and blue come from nitrogen. The southern boundary of the aurora is the visible edge of the compression zone. When the boundary reaches Indiana, Pennsylvania, or Oregon, the compression has pushed far enough south that the funneling field lines are dumping particles into the atmosphere above those states. That's why aurora visibility maps are also compression maps. The further south the boundary, the deeper the compression. During this storm, the boundary reached far enough south to be visible from 27 states. NOAA's 3-day forecast tool was designed for a different type of storm entirely. That gap between prediction and observation is the same gap the G1 to G2 miscreated, expressed in a different measurement. Back on the ground, the compression had an electrical signature too. Power grid voltage fluctuations at northern latitudes were recorded during the G2 peak. The fluctuations come from the same magnetic disturbance that produces the aurora. As the magnetic field around Earth shifts, long metal conductors on the ground experience changing magnetic flux. Changing flux induces current. That's basic physics, the same principle that runs every electric generator ever built. The difference is that the conductors in question are power transmission lines, not generator coils. The induced current flows through the transmission lines uninvited. Grid operators see it as voltage fluctuation at substations and transformers. At G2, the fluctuation is small enough that the grid's automatic regulators absorb it, without raising alarms that would reach a customer. At higher KP levels, the same mechanism pushes harder. The current grows, the fluctuations grow, the grid's automatic regulators work harder. Past a certain threshold, the regulators can't keep up, and the fluctuations reach the level where equipment damage becomes possible. The G2 threshold is below that damage point. The grid absorbed the storm, but it absorbed it across 4 separate day-night cycles, and each cycle put the same equipment through the same stress. Power transformers don't fail the way a light bulb fails. They degrade. Every heating cycle shortens the lifespan of the insulation inside the transformer core. Every current surge heats the core slightly. The grid's transformers are designed to handle normal load cycles for decades. They're not designed to handle repeated geomagnetic stress on top of normal load. Most of them were built before geomagnetic stress was a routine design consideration. Every one of those systems responded to a storm the forecast tool didn't fully predict. 27 is the Aurora number, and the Aurora is the part of this storm that went viral. Photos from backyards in Pennsylvania, time-lapse footage from Indiana, a red glow visible over Oregon farmland. That coverage was accurate. It was also incomplete. Most coverage of this storm focused on where you could see the northern lights. 20 states, then 27. The Aurora is a side effect. The main event was electrical. The same magnetic fluctuation that lit up the sky pushed electrical current through every long metal power line in the northern United States, uninvited, unscheduled, and unmetered. Those currents do not flip a switch off. They heat transformer cores slightly. Over time, repeated G2 and G3 events do to a transformer what decades of heavy use do. They shorten its life. The transformer serving your neighborhood is likely between 25 and 40 years old. GICs at G2 level are manageable. At G4 or G5, the same process has caused confirmed transformer failures. The acronym for the current is GIC. It stands for Geomagnetically Induced Current. Engineers use that term because the current is generated by a magnetic field that's shifting, not by a power plant or a battery. The source of the shift is the compressed magnetosphere above. The receiver of the current is the long metal conductor on the ground. Any conductor long enough to span meaningful distance between 2 points on the ground picks up the current. Power transmission lines are the longest continuous metal conductors in any country. A single high-voltage line can run hundreds of miles. Every mile of that line sees the shifting magnetic field above. Every mile contributes a small amount of induced current to the total. The longer the line, the more current the line carries from the storm. The current flows into transformers at the ends of those lines. A transformer is built to handle alternating current at a specific frequency. In the United States, that frequency is 60 Hz. GIC is not alternating at 60 Hz. It's essentially direct current from the transformer's perspective, or very low-frequency current. The transformer core was not designed for that kind of input. When direct current flows through a transformer designed for alternating current, the core saturates. Saturation is the technical term for a magnetic core reaching its limit. When the core saturates, it heats. Heat degrades the insulation inside. Repeated saturation accelerates the degradation. The transformer still works. It just ages faster than it would without the stress. A large power transformer costs between $3 and $10 million, according to the Department of Energy's 2023 Grid Infrastructure Assessment. The United States runs approximately 2,000 of them. The DOE's assessment puts average age at 25 to 40 years for the large transformer fleet. A typical design lifetime for a transformer is 40 years under normal operating conditions. Geomagnetic stress shortens that lifetime. Replacement isn't fast. The Department of Energy's Grid Security Office puts manufacturing lead time for large transformers at 12 to 24 months. These aren't off-the-shelf items. Each one is built to specification for the substation it serves. The specification covers voltage, capacity, cooling, and physical dimensions. A substation designed around a 500 kV transformer can't drop in a 345 kV unit without major modifications to the rest of the equipment. The global manufacturing capacity for large power transformers is limited. Only a handful of facilities worldwide produce them at the scale US utilities need. A utility that needs to replace several units at once joins a queue that may already have a 2-year backlog. If multiple utilities need replacements at the same time, the queue grows. That's the infrastructure context behind the grid effect of every geomagnetic storm. The grid holds, the transformers age. The replacement queue sits at the limits of global manufacturing capacity. The margin that let the grid absorb this G2 quietly exists because the transformers are still within their operating range. The margin shrinks every year the transformers get older. Satellite effects are the second ground-level consequence. Low Earth orbit satellites altered their orbital trajectories during this event. Ground stations had to calculate and apply corrections. Those corrections aren't optional. A satellite whose orbit is off by even a small amount drifts out of the window it's supposed to serve. A communications satellite misses its ground footprint. An imaging satellite takes pictures of the wrong area. An ISS supply run hits the wrong rendezvous point. The corrections themselves cost propellant. Every satellite launched has a finite amount of fuel for holding position and making orbital adjustments. Fuel burned during a geomagnetic storm is fuel that can't be burned for a planned maneuver later. The mission lifetime shortens by the same amount of propellant the storm consumed. AR-4419 entered the Earth strike zone while this storm was still running. For a large constellation operator with hundreds of satellites, the cumulative effect of a 4-day storm is a measurable reduction in total fleet lifetime. Not catastrophic, measurable. The operator accounts for it in fleet planning. GPS signal degradation is the third consequence the Aurora coverage didn't center. The signal degradation is measurable accuracy reduction, not total loss. That distinction matters. A GPS signal that drops is obvious. The receiver says no signal. A GPS signal that drifts is not obvious. The receiver reports a position. The position is off by a few meters. The user doesn't know. Navigation apps rely on GPS. Driving directions rely on GPS. Agricultural equipment with GPS-guided steering relies on GPS. Surveying equipment relies on GPS. Financial transactions that use GPS time-stamped records rely on GPS. A drift of a few meters affects each of those differently. A driver might not notice. A farmer guiding a tractor down a row might notice within a single pass. A financial institution time-stamping trades might not, because the drift in timing at ground level is typically small enough to stay within tolerance. The compounded effect across every GPS-dependent system is small at G2 and grows at higher KP levels. Airline operations felt the storm in a less covered way. High-frequency radio communication between aircraft and ground stations uses the upper atmosphere layer where radio signals bounce. When that layer is disturbed by a geomagnetic storm, the reflection characteristics change. Transpolar flight routes, which rely on high-frequency radio because satellite coverage at extreme latitudes is limited, sometimes reroute during significant storms to maintain reliable communication. Rerouting adds flight time and fuel. During this G2 event, NOAA's Space Weather Prediction Center documents high-frequency radio interference on polar flight routes as a confirmed G2 effect. The rerouting decisions during a G2 are operator-specific. Some airlines reroute, some accept the interference, and maintain the shorter polar path. The decision depends on the carrier's risk tolerance and the specific conditions measured. Pipeline operators also monitor for GIC effects. Long metal pipelines carrying oil or gas act as conductors just like power lines do. The induced current in a pipeline doesn't cause immediate failure. It affects cathodic protection, which is the electrical coating that stops buried steel pipes from rusting. During a strong geomagnetic event, the cathodic protection readings shift, and operators adjust their monitoring to compensate. At G2, those adjustments are routine. Railroad signal systems are another long conductor network vulnerable to geomagnetic induction. Signal systems use electrical currents in rails to detect train presence. GIC can introduce false readings. NOAA's Space Weather Prediction Center documents rail signal interference as a confirmed G4 and above effect. At G2, the railroads monitor for it, but no false signals were confirmed during this event. The grid, the satellites, the GPS signal, the airline routes, the pipelines, the rails. Every one of those systems carries a thread of the same event. The Aurora coverage saw one thread. The storm had at least 6. The last G4 storm burned out transformers in Quebec in under 90 seconds. March 13th, 1989. March 13th, 1989. That's the date of the Quebec blackout. A G4 geomagnetic storm hit the Canadian power grid, and the Hydro-Quebec transmission system collapsed in 90 seconds. 6 million people lost power. The blackout lasted 9 hours. The transformer damage took 2 years to fully repair. Hydro-Quebec estimated total losses from the blackout at over $2 billion in 1989 values. That event lasted less than a day. This event lasted 4. The public understood this storm as a weekend storm, something that hit, produced Aurora, and passed. The storm ran 4 days. 4 consecutive days of geomagnetic disturbance means every GPS satellite in orbit corrected its trajectory 4 times. Every northern latitude transformer absorbed GIC current across 4 separate night cycles. 4 cycles of the same stress is not 4 times one event. It's compounding. NOAA issued alerts per event. No agency issued a 4-day cumulative stress advisory. Grid operators managed each day as a separate alert. Nobody sent a single communication saying this is 4 days of the same pressure on the same systems. There is one event in the historical record that lasted longer than 4 days and cost more than any natural disaster in Canadian history. CME-driven storms typically last 12 to 36 hours. That's the usual duration when a coronal mass ejection hits Earth. The ejection is a discrete event. It arrives, compresses the magnetosphere, and moves past. The magnetic field recovers over the following day. CHHSS storms paired with CIRs can last 3 to 5 days. The stream is continuous for as long as the coronal hole stays in an Earth-facing position. As the Sun rotates, the hole eventually rotates off the Earth-facing disk and the stream tapers. For a hole in the right position, the stream duration can run most of a week. This event confirmed 4 days, April 17th through April 20th. That's on the long end of typical CHHSS duration, and equal to the upper bound of what the agency classifies as a sustained event. The distinction between a single event storm and a sustained storm matters because every system that absorbs the stress absorbs it differently across duration. A single CME impact stresses a transformer once. The transformer heats during the event and cools afterward. A CHHSS paired with a CIR stresses the same transformer across multiple day-night cycles. The transformer heats, cools partially, heats again, cools partially, and repeats. The repeated cycle is harder on the insulation than a single larger stress of equivalent total energy. Grid operators managing this kind of sustained event can't just run one response. They have to run 4. The response cost is 4 times the response cost of a single-day event. The margin in the system is tested 4 times instead of once. Satellite operators face the same multiplication. A single drag event requires 1 correction. A 4-day drag event requires corrections on each orbital period the satellite passes through the disturbed zone. A low Earth orbit satellite completes an orbit in roughly 90 minutes. NOAA's drag documentation confirms that extended CHHSS events force repeated correction burns across multiple orbital passes. Not every pass requires a correction, but any pass where the drag exceeds the satellite's tolerance does. Across a constellation of hundreds of satellites, the number of required corrections grows into the thousands across a 4-day event. Each correction consumes a small amount of propellant. The total propellant consumed across the event is significant for mission planning. Operators track the consumption as a budget item and report it after the storm. The reporting isn't immediate. Post-storm assessments take days or weeks to compile. The public rarely sees the numbers. They appear in industry publications and internal operational reviews. The aggregate effect across all constellations during a 4-day event is not currently reported in a single consolidated source. NOAA's public alert system issues watches, warnings, and alerts on a per-event basis. That's the design. When the geomagnetic KP reaches a threshold, an alert goes out. When the disturbance drops below threshold, the alert clears. If the KP rises again the next day, a new alert is issued. The system treats each rise above threshold as a separate event. For a 4-day CHHSS storm, the system issues alerts on each night the KP peaks. Grid operators receive those alerts as discrete events. The agency does not currently issue a consolidated multi-day cumulative impact advisory for sustained CHHSS events. The gap is structural, not an oversight of a particular storm. A cumulative advisory would aggregate the stress across multiple days. It would inform grid operators that the transformers absorbing GIC tonight have already absorbed GIC for the previous 3 nights, and that the cumulative stress on the insulation is higher than any single-day alert would suggest. That kind of communication would change the operational response. Without it, each day's response starts from baseline, as if the previous days hadn't happened. This is the broken system. The system was designed to issue per-event alerts. It did that. The system was not designed to communicate cumulative stress across sustained events. It didn't. Both statements are true. The gap is the gap. For the viewer watching from Minnesota, Michigan, Wisconsin, or any state with a significant share of aging transformer infrastructure, the 4-day cumulative stress sat on the local grid without a communication acknowledging the cumulative nature of it. The grid operator saw the individual alerts. The public saw the Aurora coverage. Nobody in the public communication chain said, "This is day 3 of 4, and the transformers you rely on have been absorbing induced current across every one of those nights." Satellite drag compensation burns consume propellant reserves. That reserve is a fixed quantity set at launch. Every burn reduces what's left. The reduction affects how long the satellite can maintain its orbit at the end of its designed lifetime. NOAA's drag documentation confirms that extended CHH-S events require enough correction burns to measurably reduce a satellite's remaining fuel supply, shortening its operational life. For a commercial constellation operator, that translation runs into real cost. Replacement satellites have to be launched earlier than planned. Launch slots are scheduled years in advance. Moving a replacement launch forward isn't always possible. Some satellites simply end their missions sooner. GPS satellites sit at a higher altitude than the drag-sensitive low Earth orbit zone. The GPS constellation doesn't face significant drag issues at G2 levels. Its exposure to the storm comes through the compressed magnetosphere around it and the disturbed upper atmosphere below it, which bends and delays GPS signals. The constellation operator monitors signal integrity and applies corrections through ground-based GPS correction stations when necessary. Those corrections are continuous during a storm. Across 4 days, the ground-based GPS correction stations ran continuous corrections on the GPS signal. The receivers in cars, phones, and surveying equipment received a partially corrected signal for the full event duration. Users didn't see a dashboard light warning them. The systems handled the correction in the background. The Quebec blackout lasted 9 hours. The damage took 2 years to fully repair. The coronal hole that caused this storm was still open. Hydro-Quebec's transformers absorbed 9.4 gigawatts in under 90 seconds. 9.4 gigawatts. That's the size of the electrical surge Hydro-Quebec's grid absorbed on March 13, 1989, before the system collapsed. For context, 9.4 gigawatts is roughly the electrical output of 9 large nuclear reactors running at full power, delivered to a grid not designed to absorb it in under 90 seconds. That figure is the worst-case ground-level consequence of a geomagnetic storm on record in North America. This April event didn't approach that figure. It wasn't supposed to. G2 is several steps below G4 on the KP scale, and the grid absorbed the induced current inside its normal operating margin. The Aurora was the public face of the storm, but the Aurora across 27 states wasn't just a photograph opportunity, it was a live map. NOAA's Space Weather Prediction Center uses real-time Aurora oval maps to measure where the magnetosphere is most stressed during any given event. The Aurora oval is the ring of auroral activity that sits over the polar regions under quiet conditions. During a storm, the oval expands southward. The southern boundary of the oval marks the edge of the compression zone where Earth's shield has been pushed closest to the planet's surface. The boundary isn't the same at every longitude. It shifts based on which parts of the magnetic field are taking the most pressure from the solar wind at a given moment. During this event, the southern boundary extended into Pennsylvania, Indiana, and Oregon, at various points across the 4 days. Those 3 states mark the deepest southward penetration the boundary reached. That map is a live X-ray of shield failure. The aurora visible in a Pennsylvania backyard was the signature of the shield, compressed closer to the surface above Pennsylvania than it had been in several years. The aurora visible in Oregon was the signature of the same compression over the western Pacific magnetic sector. The boundary moved with the stream, and it mapped the stream's pressure in real time. Forecasters use aurora oval maps alongside satellite magnetic field sensor data to understand the storm's geometry. A compressed oval over a specific longitude means the shield is weaker there. A compressed oval over multiple longitudes at once means the entire sunward hemisphere of the magnetosphere is under pressure. During the peak of this G2, the oval compressed across most of the North American and Pacific sectors simultaneously. That's what produced the state count of 27. For aurora enthusiasts, the map is a viewing guide. For grid operators, it's an operational risk map. For satellite operators, it's a drag exposure map. The same measurement serves 3 different users, each reading the same boundary for a different purpose. The southern boundary during this event mapped the exact zone where Earth's shield compressed closest to the surface. AR 4419 produced 16 flares in 24 hours, every one fired away from Earth. It's 3 days from the center of the Earth strike zone. R4419 is the designation for an active region on the Sun. Active regions are areas of complex magnetic activity, typically centered on sunspots. The number is assigned by NOAA, as each active region rotates into view on the Earth-facing hemisphere. AR4419 is currently the largest visible active region on the Sun's Earth-facing hemisphere, and it's been tracked for several days as it moves across the solar disk. Each active region has a magnetic classification. The classification describes the arrangement of the magnetic poles within the region. Simple regions have one positive pole and one negative pole cleanly separated. Complex regions have multiple poles intertwined. The more intertwined the field, the more energy stored in the region, and the more likely the region is to produce a major flare. NOAA's solar region. Summary during the storm period classified AR4419 as beta-gamma, which means opposing magnetic poles packed close enough to store explosive tension. The field lines cross and twist around each other. When the twist reaches a critical point, the region releases energy explosively as a solar flare. The classification sits one step below the most dangerous magnetic tangle type, the one most strongly linked to X-class flares. AR4419's position on the solar disk is rotating towards center. The central position is the Earth strike zone. Any flare fired from an active region near the center of the disk has a high probability of sending its ejected material toward Earth. Flares from the edges of the disk send their fired material off to the side. The closer to center, the more direct the strike. The Sun's rotation as seen from Earth takes approximately 27 days to complete. An active region crossing the disk is visible for about 14 days. The central portion of that transit, roughly 7 days on either side of the meridian, is the Earth strike zone. A flare fired during that window has a reasonable chance of producing an Earth-directed coronal mass ejection. It has 4 to 7 days left before rotation carries it out of the strike zone. NOAA's solar region. Summary confirmed AR4419 produced 16 flares in a 24-hour tracking window during this event. Every one of them was C-class or below. C-class flares are the third smallest category. They can cause minor radio blackouts but don't typically produce Earth-directed geomagnetic storms. M-class and X-class flares, which are 1 and 2 categories stronger, can produce significant to extreme effects if they're Earth-directed. 16 flares in 24 hours is a high rate of activity. The rate tells you the region is magnetically active. The beta-gamma classification tells you the region has the field structure to produce a stronger flare. What the rate doesn't tell you is when or whether that stronger flare will arrive. The mainstream framing of AR4419 in most space weather coverage has focused on the flare count and the classification. What's received less attention is the timing of the Earth strike window. A region producing 16 flares per day while it's pointed away from Earth is less concerning than the same region producing a single M-class flare while it's pointed directly at Earth. The direction matters more than the count for any individual event. AR4419 is rotating into the position where direction and magnetic complexity could align. NOAA's tracking does not include a prediction of whether AR4419 will produce an Earth-directed major flare during its central transit. The agency tracks the region and reports classifications. It does not predict specific flares in advance. That's a technical limit of current solar forecasting, not an agency choice. The Aurora oval's southern boundary mapped where Earth's shield was weakest during this G2. NOAA's technical documentation puts full magnetospheric recovery after a G2 at several days. AR4419's Earth strike window runs for several days. Those timelines overlap. A major flare from AR4419 wouldn't arrive instantly. Light from the flare reaches Earth in 8 minutes. The energetic particles that accompany the flare take between 15 minutes and several hours. The coronal mass ejection, if one is produced, takes 1 to 3 days to cross the distance from the Sun to Earth depending on its speed. That travel time is the warning window for ground-based systems. NOAA's warning for a CME impact runs 15 to 60 minutes before ground-level geomagnetic effects peak, based on measurements from satellites at the L1 point. The longer interval covers slower CMEs. The shorter interval covers the fastest. For AR4419 to produce a direct ground threat in the next week, the region would need to fire an M-class or X-class flare. While its position is Earth-directed, the flare would need to produce a coronal mass ejection, and the ejection would need to have an Earth-directed trajectory. Those conditions have not been met as of the confirmed data covering this event. The rotation carrying the region to the meridian continues. The Earth strike zone is a 7-day window. 3 days remain. AR4419's Earth strike window has 3 days left. Whether it fires toward Earth during that window is not confirmed. What is confirmed is the exposure a viewer in the northern United States already absorbed from the storm that just passed. A viewer in Pennsylvania, Ohio, or Minnesota watched Aurora last weekend. The storm felt distant, harmless even. The same storm drifted their GPS position by meters. A meter on a highway is the difference between your lane and the next one. GPS-assisted lane correction systems in vehicles made after 2018 were operating on a signal that was measurably off. The viewer's car, their navigation, their grid, all ran on degraded inputs for 4 days. Not catastrophically, but not at full specification either. The same coronal hole rotates back into firing position in 23 days. GPS drift under G2 conditions measures in the range of a few meters for consumer receivers. That's the confirmed accuracy degradation during this storm. The degradation isn't a signal loss. The receiver locks onto the satellites. The position it reports is off by a small amount. The user sees a map position that looks normal and drives as if the position is correct. For a driver using a navigation app, a few meters typically doesn't matter. The app's turn-by-turn instructions account for normal GPS noise. The navigation works. For a driver using a vehicle with GPS-assisted lane correction, the calibration matters more. Lane correction systems use GPS as one input among several. Cameras and sensors provide the main lane detection. GPS provides context about road geometry and speed. If the GPS signal drifts by a few meters, the context is off. The system still works, but the calibration between inputs is slightly degraded. Most lane correction systems in production are designed to tolerate normal GPS error. During a G2 storm, the error exceeds normal by a small margin. The systems handle it. But the systems are handling it. They're not operating with clean inputs the way they would on a day without a storm. For a driver using GPS-assisted collision avoidance, the picture is similar. The camera and radar do most of the work. GPS provides backup context. Degradation of the GPS signal shifts the backup context slightly. The primary systems compensate. The compensation isn't automatic across every model year or manufacturer. Older systems have less margin. Newer systems have more. A driver in a 2019 vehicle likely received effective compensation. A driver in a 2016 vehicle with first-generation lane assist might have seen the compensation degrade more visibly. Pacemaker remote monitoring systems use cellular networks linked to GPS timing. During this storm, GPS timing shifted by seconds. For standard remote monitoring, that shift stayed within tolerance. The viewer with a pacemaker received the same effective care on every one of those 4 days. Power grid voltage fluctuations at northern latitudes were confirmed during this G2 event. The fluctuations were within the grid's normal operating margin. Nobody lost power because of the storm. That's the confirmed outcome for the grid at G2. The northern US grid covers states from Minnesota through New England. It includes transmission lines, substations, and transformers that serve tens of millions of residential and commercial customers. The infrastructure is aging. Those are the same transformers that absorbed 4 nights of GIC current last week. A G3 event pushes GIC levels well above G2, as the KP scale is not linear at these levels. 3 times the current isn't 3 times the damage. Transformer response to GIC has thresholds. Below certain current levels, the response is small. Above the thresholds, the response grows rapidly. NOAA's Geomagnetic storm scale documents that G4 conditions produce roughly 10 times the GIC current of G2 conditions. KP8 is 2 steps above KP6. The cumulative current at G4 sits in a range where transformer saturation becomes a routine consequence across the northern grid, not an exceptional one. NOAA's warning system for grid operators currently provides 15 to 60 minutes of advance notice for CME impacts. That's the window between the L1 satellite measurement and the peak effect at Earth. For a fast CME, the window is shorter. For a slower CME, longer. For CHHSS events like the one that just passed, the warning comes earlier. The watch is issued 1 to 3 days in advance, based on the coronal hole's Earth-facing geometry. That's a much longer lead time than a CME provides, but the longer lead time comes with a trade-off. The intensity prediction for CHHSS events is less precise. The intensity can upgrade during the event without a corresponding upgrade to the public watch in time to change operational response. This event demonstrated that gap. The watch was issued at G1. The storm arrived at G2. The upgrade happened after impact. For grid operators preparing responses based on the original watch, the response was calibrated for a smaller storm than they received. The viewer in Wisconsin or Michigan didn't see that gap directly. The gap was absorbed by the grid's operational margin. The transformers serving their neighborhoods handled the extra stress. The transformers are the same transformers that will be handling whatever comes next. The next firing is not far away. The coronal hole that caused this storm returns to Earth-facing position in 23 days. The Sun's rotation carries features across the Earth-facing hemisphere on a predictable schedule. If the hole is still present and active when it returns, the stream it produces could match or differ from this event. The hole may shrink, it may grow, it may close entirely. Solar observers track it through each rotation. 23 days is a short planning window for infrastructure response. The transformers that absorbed 4 days of GIC stress this week will still be in place. The forecasting tool that underpredicted this event by 1 kp level will be the same tool providing the next forecast. The warning gap will not have closed in 23 days. AR4419 is a different threat on a different timeline. The active region's Earth strike window closes in 5 to 7 days from the current date of the storm's ongoing activity. If AR4419 produces an Earth-directed major flare during that window, the impact would arrive on top of a grid that just absorbed a 4-day CHHSS stress event. The two events don't combine physically, but they combine as operational load on the same equipment. For the viewer, the realistic personal stakes of this storm and the next week's look like this. GPS-dependent services may see intermittent small accuracy shifts. Regional grids in the northern US may see voltage fluctuations within their operating margins. Satellite-dependent services may see small delays in data delivery. None of those effects require the viewer to take action. The scenarios that would require action are G3, G4 and G5 events on aging infrastructure. Those scenarios are not predicted for the immediate window, but the infrastructure readiness for those scenarios is the same infrastructure readiness that exists today. No upgrades will happen in the next 23 days. No transformers will be replaced in that window. No forecasting tool will be recalibrated. According to NERC's grid reliability assessments, a G4 event on the current northern US grid would produce GIC levels the modern infrastructure has not been designed to absorb. The Quebec 1989 event affected the Quebec grid specifically. The US northern grid's integrated response to a G4 on modern aging infrastructure has not been tested at full scale. The personal stake for the viewer aged 55 to 70 in the northern US is that the systems they rely on for daily life operate on margins that absorb this G2 without visible disruption, and those same margins face an unknown return schedule. The coronal hole rotates back. AR4419 remains in the strike window. The grid operates on the equipment it has. AR4419 reaches the center of the Earth strike zone in less than 72 hours. Less than 72 hours. That's the countdown for AR4419's arrival at the center of its Earth strike position. It's also the window during which the region's beta-gamma magnetic complexity will have its most direct geometric alignment with Earth. Whether the region fires an Earth-directed major flare during that window is not predictable in advance. What is confirmed from the event that just passed carries its own weight. The G2 storm was stronger than NOAA's own forecast predicted. The CIR and the CHHSS combined to push the KP index one full level above the G1 prediction. GPS signal degradation occurred across the United States during the peak. Satellite drag on low Earth orbit spacecraft increased enough to require operator corrections. Power grid voltage fluctuations were recorded at northern latitudes. The Aurora reached 27 states, 7 beyond the original forecast. The storm remained active through April 19th, with elevated readings carrying into April 20th. That's 4 days total. What is not confirmed is the cumulative stress absorbed by aging northern US transformers across the 4-day event. No post-storm cumulative grid stress report has been issued. Individual utilities monitor their own equipment and report internally. Industry associations compile aggregate reports over weeks or months. No single federal agency has published a consolidated post-event infrastructure assessment covering the northern US grid's response to this specific CHHSS storm. 4 days of GIC stress on those transformers, and no agency has published an assessment of what they absorbed in total. What is also not confirmed is whether AR4419's rotation through the Earth strike zone will produce an Earth-directed flare. The active region's window of maximum Earth-facing exposure closes in 5 to 7 days from the most recent position report. The region could fire an M-class or X-class flare during that window. It could fire only smaller flares. It could rotate out of the zone quietly. All 3 outcomes remain possible. The same coronal hole that fired this event will rotate back into an Earth-facing position in approximately 23 days. Whether it's still active and producing a high-speed stream at that point depends on whether the hole has shrunk or closed during the rotation. Coronal holes can persist for multiple solar rotations. They can also close within weeks. Solar observers will track the hole's development through the next rotation. NOAA's space. Weather Prediction Center acknowledges the CIR pairing limitation in its published technical documentation, and no operational upgrade timeline for the public forecast tool has been announced. The forecasting gap that underpredicted this event by 1 kp level will remain in place for the next return of the same hole. Whether a similar underprediction occurs depends on whether the CIR pairing geometry repeats. The agency acknowledges the CIR pairing effect as a known limitation in its technical documentation. Upgrading the public 3-day forecast tool to incorporate CIR density weighting more accurately is a research and development task. It requires instrument calibration updates, model code changes, and operational validation. The timeline for that work has not been published. For the viewer, the personal proximity systems that absorb this storm are the same systems that will face whatever comes next. The GPS satellites in orbit are the same satellites that corrected their drag burns during the storm. The grid's operational margin is the same margin that absorbed the 4-day stress. No federal communication has advised the public of any change risk level following this event. The emergency management protocols in place before the storm are the protocols in place after it. NOAA's alert system will continue to issue watches and warnings on a per-event basis. The multi-day cumulative impact advisory format does not exist, and there is no published schedule for its creation. The transformer at the substation nearest your neighborhood absorbed 4 nights of uninvited current. Its condition before April 17th is the same condition it carries into whatever comes next. The transformers, the satellites, and the GPS network that would absorb a G4 are the same ones that just absorbed 4 days of G2. The communication channels that would warn about them are the same channels that underpredicted the storm that just passed. The systems worked at G2. The grid has margin for a 1-level forecast miss. That margin doesn't hold at G3 or G4. The same forecasting tool issues the next watch. The next watch covers the same infrastructure. The gap between the public watch and the actual storm is the single most important fact in this event. Not the Aurora count, not the state list, the gap. A 1-level miss at G2 is manageable. A 1-level miss at G4 is not. The gap exists because the forecasting tool underweights a known mechanism. The mechanism is the CIR pairing with the CHHSS. The tool has not been updated. NOAA's Space Weather Prediction Center has confirmed the CHHSS forecasting limitation. No upgrade schedule has been published.